Okay, so today I'm going to go through the lesson. The simulation within the lesson is a little hard to follow, so I wanted to make sure to make it really clear and kind of just walk you right through it so that you could really get the good out of it and understand Rutherford's gold foil experiment. So hopefully you've already done your bell ringer, reviewing the models that we've talked about and that you should know about pretty soon. Democritus, remember, was the Greek philosopher. He was just a thinker walking on the beach one day, said, sand falls apart. I wonder if other things do. And then he developed his theory a little bit, but he didn't have any evidence. John Dalton had the billiard ball model. He had, he thought that it was just a sphere, just a ball, a hard, dense ball. He had 4 postulates that we talked about in the last lesson. But if you notice how the model develops from a thought to we think of it as a ball to J.J. Thomson's discovery of the electrons right here in the plum pudding model. We called it the chocolate chip cookie model. Little specks of negative pieces on the positive cookie part. And then we come to the nuclear model, which is what we know today. Ernest Rutherford found that there's a nucleus and that there's space in between the nucleus and the outside of the atom. That nuclear model kind of evolved into a planetary model with Niels Bohr. Niels Bohr said that electrons travel in a pattern, like an orbit, like planets around the sun. And then his model was both proven and expanded upon by Erwin Schrödinger. It says Edwin on this picture, but it's Erwin Schrödinger and de Broglie and Heisenberg. So the model continues to grow. But the big jump was from being a mass, a ball, to a mass with specks on it, to having a lot of empty space. There was lots of parts to the atom, and that's where Ernest Rutherford come in. So today we're going to investigate Ernest Rutherford's gold foil experiment. Today you're going to answer questions. You can use the Cami upload. Here's the PDF, or there's a Google Doc of the file as well. So I am going to model using the Google Doc. That is your choice. I know a lot of people think the Google Doc is just easier to deal with. So I'm going to open in a new tab. When you come to the Google Doc, you will want to make a copy of that. You're not able to type on this one because if you were, then one person would fill it out and everybody else would get all of the answers. So you're going to go File, Make a Copy. You're going to put that in your drive. It's really nice if you change the copy of to your name. And then hit OK. I'm going to close the original one. Yeah, so now we have something we can type on. So we're going to go through these instructions together. It says go to fet.colorado.edu. This is the simulation that is embedded in today's lesson. Okay, so if I go, there is the simulation that is embedded in today's lesson. So I'm going to go ahead and make this full screen and we will walk through the questions together. So when I look at this, it's kind of hard to see the purple tracing lines. I'm going to go ahead and hit reset so that you can see how it opens when you open it. In the instructions to your lesson today, it says in the simulation, click on the plum pudding atom square. Okay, we're going to start with the plum pudding model because that's what J.J. Thomson discovered, and that's what he thought the atom looked like. Everybody else thought that too. And so what do you notice? What do you notice about if you are doing this on your simulation, you may have to click the traces box so that you can see the lines. But these alpha particles that we're looking at, that's what is being shot across the atom. These alpha particles are all traveling in a straight line. That is what that's what Rutherford thought they would see when they looked at their evidence, is that they'd see a bunch of straight line hits. If we look right here, we have an alpha particle emitter, just like Rutherford used, sort of. And it is shooting alpha particles at a gold foil. And that gold foil, they thought that right behind it, they would see a bunch of dots on their x-ray paper, and they would see all in a straight line. But what they found out was way different. So go ahead and answer number 1, where it's asking you what type of path do the alpha particles take. You're seeing it's a straight line path. Okay? You can hit pause if you need to, but I'm going to go ahead through the instructions. It says click the Rutherford atom square. So that's right down here at the bottom, Rutherford atom square. Set the number of protons to 20. So I'm going to come over here, atom, protons. We're going to make that 20. I'm going to go ahead and make my neutrons 20 just because it'll make it easier to look at in a second. And click on the blue button above the alpha particles to start firing alpha particles toward the gold foil. Okay, so right here's my blue button. I'm going to start firing alpha particles. Now all I see is purple dots right now, so I need to click the traces button. Okay. And that's what number 1 says. Click on the traces button. What do you notice about the paths of most of the particles? Look at these purple lines. The paths are mostly straight. When you get to one that goes really close to a nuclei, it veers off. Here's another one. Veers off a little bit. And then it says, so that's number 1. It's straight lines. We're going to increase the number of protons. So here's number 2 to 60. You can also slide. So when we increase it to 60, we notice, looks like those are veering off even greater. Looks like the lines are have a little stronger bend to them. That's number 2. You can hit pause and answer that. Number 3, now increase the number of protons to 100. So I'm just sliding the number of protons over to 100. Whoa, those are really deflecting. They're really moving away. Number 3 says, how does this increase change? How does it change how the alpha particles move through the gold foil as compared to when you started? Why do you think this change occurred? Well, this is where Rutherford was. He's like, well, what happened? I don't know. He was concerned. He had to figure it out. And what he knew was that alpha particles are positively charged. The nucleus, he didn't even know existed. He thought it was that plum pudding model. So he's looking at this and he's going, all right, some of these go straight through. And I see on my x-ray paper that would have been out here, there's straight through lines. But some of them get deflected off. Even that one went straight backwards. So he had to think, well, what would make a positive particle deflect or reflect or move away? He concluded that it had to be another positive particle. If you think about a magnet or you think about charges, likes repel, opposites attract. So that repulsion proved to Rutherford that there had to be another positive thing inside the atom, and that's how he came up with this idea of the nucleus. Back to number 3 is asking you, how does it change? How did the pattern of these alpha particles change? You can see that it just bends way more. It gets reflected way more. Number 4 says repeat the above steps, but now vary how many neutrons are present with the protons. Does this change how the alpha particles travel? All right, so we had 22 neutrons all the time. Let's go back and look at what does 20 protons and 22 neutrons look like. Okay, 60 protons and 22 neutrons. We saw that already. The bending in the traces goes way deeper, a much bigger bend. We go neutrons, increase those to 60, around 60. I don't see that much difference. What if we make the neutrons a whole bunch? It's not quite as steep of a deflection there. At about 100 protons, that deflection is pretty strong. But if I have no neutron, like little bit of neutrons and 100 protons, what's going to happen? Deflection is pretty strong. So it doesn't look like the neutrons really change the pattern very much. Number 5 says, click on the red or gray sphere and reset the number of protons to 20. Okay, so we're going to look at our simulation. Here's the red and gray sphere. This is actually showing you up close on the nucleus. We're going to return the protons to 20 and look at what happens. So this is the nucleus of the atom that these alpha particles are being shot at. All right, so there's 20. Well, let's look at 60. And that should be number 5. You're seeing the same thing. You're seeing a slight deflection. As soon as the alpha particles move towards that nucleus, they kind of get thrown away. Number 6 says click on the red or gray sphere. We already did that. And reset the number of protons to 60. So we're going to go to 60 like we did before. But this time we're looking at the nucleus of what is being, alpha particles are being shot at. We can see that deflection really well now. Let's go up to 100 protons just to look and see what it does. And that is number 7. Now increase the number of protons to 100. Watch and describe how the alpha particles move in relationship to the nucleus. They are like trying to get as far away from that as possible because this is a positive 100 charge. A positive 2 charge, which is an alpha particle, doesn't want to have anything to do with it. Just like 2 north ends of a magnet, they're going to repel each other. Okay, number 8, you just want to think about 6 and 7. Number 9, how is the plum pudding model different from the Rutherford model of the atom? So what we saw is we saw that deflection of the alpha particles in the Rutherford model. With the plum pudding model, let's go back and look at that. We notice that the straight line movement, there's only straight lines. There's no deflection of any nature. So that's that one. Why do you think that our model of the atom changed after Rutherford's experiment? So looking at Rutherford's experiment, this is what he found. So he had evidence to change. He had evidence that there had to be something dense and positive in the middle and then some space, because some of them did go straight through. And so you can see that when we go back to 20 protons, you can see some of them go straight through. Right exactly like Rutherford expected. But some of them are deflected. So because some of them are deflected and some of them go straight through, there had to be empty space there. And then why were the alpha particles deflected by the nucleus and not attracted to it? Well, if alpha particles are positive and the nucleus is positive, they're not going to attract one another. They're the same. Sames repel. So they're going to repel each other, and that's where we see this deflection right here.